The end of the universe may not begin with a collapsing star, a collision, or any event that a telescope could see. It could begin in empty space. At some point, in some region with no special warning and no obvious cause, the vacuum itself could change state. A microscopic bubble would appear. Inside it, space would occupy a lower energy configuration than the one surrounding it. The bubble would expand, driven by the energy difference between those two states, and its boundary could accelerate to nearly the speed of light. Anything reached by that boundary would enter a different physical environment. Particle masses could change. Forces might no longer behave as they do here. Atoms, chemistry, stars, and living depend on the specific properties of the fields filling our universe. Alter those properties enough, and ordinary matter would not be damaged in any familiar sense. The conditions that allow it to exist would simply no longer apply. There would probably be no useful advance signal. Light from the approaching boundary could not arrive much earlier than a wall, moving at almost the same speed. No observatory would watch it, crossing the galaxy. No instrument would measure a countdown. The first local evidence would also be the event itself. That description sounds like an invented catastrophe. The underlying mechanism, however, comes from ordinary quantum field theory. It is called vacuum decay. There is no evidence that such a decay is approaching. Calculations based on the Standard Model generally suggest that, even if our vacuum is metastable, its expected life is enormously longer than the current age of the universe. Unknown physics could also remove the instability entirely. The danger is not the prediction of an imminent ending. The more difficult point is that physics has not established that our present form of empty space is the most stable state available. In daily language, vacuum means the removal of matter. Pump the air from a chamber, and what remains is called empty. Quantum theory does not permit that simplicity. Even a region containing no particles is filled by fields. Electromagnetic fields, electron fields, quark fields, and the Higgs field are not objects placed inside space. They are part of the physical structure found at every point in it. A particle can be understood as an excitation of one of these fields. Remove the excitation, and the field remains. Its lowest energy configuration is what physicists call the vacuum. The word lowest requires care. A field can settle into a state that is lower than its immediate surroundings, without occupying the lowest possible state in the entire theory. The energy landscape may contain more than one depression. A field resting in a local minimum can appear stable because moving away from that point initially requires considerable additional energy. Yet, somewhere beyond the barrier, there may be a deeper minimum. The first state is a false vacuum. It can persist for an extraordinary length of time. It can support particles, forces, galaxies, observers, and a history spanning billions of years. None of that proves it is permanent. Quantum mechanics allows a system to cross a barrier without climbing over it through a process known as tunneling. For a vacuum field, tunneling would not require the whole universe to change simultaneously. A small region could make the transition first. If that new region were large enough to avoid collapsing back, it would become a bubble of the lower energy vacuum. The energy gained by enlarging its interior could overcome the energy stored in its wall. Expansion would then become favorable. The bubble would grow. This possibility became far more concrete after the discovery of the Higgs boson. The Higgs field has a non-zero value throughout the universe, and its interaction with elementary particles helps determine their masses. The boson detected at CERN is an excitation of that field. Measuring its properties gave physicists information about the shape of the field's energy landscape. That shape is not determined by the Higgs alone. Quantum effects from other particles alter it. The top quark matters especially because of its unusually strong interaction with the Higgs field. When researchers use measured Higgs and top quark properties, along with the strong interaction, and extrapolate the Standard Model to energies far beyond any collider, the Higgs potential may eventually bend downward. Under that calculation, our familiar electroweak vacuum is not necessarily the deepest state. It may be metastable. The conclusion remains sensitive to measurement uncertainties, particularly those involving the top quark and the strong coupling. It also assumes that the standard model can be extended across an immense range of energy without undiscovered particles or interactions changing the result. Physics near the scale where gravity becomes quantum mechanical is not understood well enough to guarantee that assumption. So the deeper vacuum has not been observed. No detector has found a bubble wall. No experiment has demonstrated that decay must occur. What exists is a narrow and uncomfortable relationship among measured particle properties, theoretical extrapolation, and a stability boundary that appears unexpectedly close. A small change in the inputs can move the universe from metastable to stable. New physics can reshape the entire landscape. The fate of empty space may depend on particles we have not discovered, forces too weak to measure, or gravitational effects our present theories cannot calculate reliably. That uncertainty cuts in both directions. The standard model may be sounding a false alarm because it is incomplete, or its incompleteness may conceal a risk that the current calculation underestimates. The universe has survived for roughly 13.8 billion years. That tells us the vacuum has lasted at least that long in our observable region. It does not tell us that the vacuum is eternal. A radioactive nucleus can persist for many half-lives without revealing when one particular decay will occur. Past survival constrains probability. It does not convert a metastable state into a stable one. Vacuum decay is therefore less a forecast than an accusation directed at one of our quietest assumptions. We treat the background of reality as fixed while everything inside it changes. Stars burn out. Galaxies merge. Black holes evaporate across unimaginable spans of time. Through all of this, space itself seems to remain available, neutral, and dependable. Quantum field theory allows another reading. The background may also be a temporary arrangement. And the evidence for that possibility does not come from the distant edge of the universe. It comes from measurements made inside particle detectors on Earth, from the masses and interactions of objects, so small that their behavior may be telling us whether reality has settled into its final state. The next question is how a particle discovered in a collider could carry information about the long-term stability of the entire universe, and why the answer depends so heavily on one of the heaviest elementary particles we know. The Higgs field is often described as the mechanism that gives particles mass. That is useful, but incomplete. A better way to think about it is as a field that has settled into a particular value everywhere in space. Elementary particles interact with that field by different amounts. Those interactions help determine the masses they appear to have. Change the field's underlying state, and the familiar inventory of matter may no longer survive in recognizable form. The vacuum is therefore not merely an empty stage. It helps write the rules followed by everything on it. In the standard model, the Higgs field is governed by an energy potential. Near the state we inhabit, the potential resembles a bowl. Disturb the field slightly and it tends to return toward its usual value. That local behavior is why the vacuum appears stable. The Higgs boast itself is one expression of those small disturbances. But the bowl may not continue rising forever. At much higher field values, quantum corrections become important. The particles that interact with the Higgs field alter the effective shape of its potential. Bosons tend to push that shape in one direction. Fermions can push it in another. Among all the known particles, the top quark exerts the strongest destabilizing influence. The top quark is exceptionally massive for an elementary particle. Its coupling to the Higgs field is correspondingly strong. In the calculations, that interaction can pull the Higgs potential downward at extreme energies. If the downward bend becomes deep enough, the familiar vacuum is no longer the absolute minimum. somewhere far beyond the scale of ordinary experiments, a lower state appears. That is the basic source of the metastability result. It is also why the answer is so delicate. The measured mass assigned to the top quark is not a perfectly simple input. Quarks cannot be isolated and placed on a scale. They are confined inside composited particles and jets of hadrons, and their property are inferred from collision products using theoretical models. The quantity extracted from an experiment must then be related to the mass definition used in high-precision vacuum stability calculations. A small shift matters. The boundary between a stable and a metastable universe occupies a narrow region in the parameter space defined by the Higgs mass, the top quark mass, and the strength of the strong nuclear interaction. Move one of those values slightly, and the long-distance behavior of the potential can change. This does not mean the universe is balanced on a knife edge in the ordinary sense. The decay time calculated within the standard model can still be fantastically long. The apparent closeness is theoretical. It concerns which side of a mathematical boundary our measured parameters occupy after they are extrapolated across scales far beyond anything humans can directly test. That extrapolation is the real pressure point. Particle accelerators probe high energies by human standards, but they remain far below the regimes where the Higgs potential may become unstable. The Large Hadron Collider can study collisions in the tera-electron-volt range. The possible turnover in the effective potential may occur at energy scales many orders of magnitude higher. No machine can reproduce those conditions directly. Instead, physicists use a procedure called renormalization group evolution. Measured interaction strengths are treated as scale-dependent quantities. The values observed at accessible energies are mathematically evolved upward. As the scale changes, the couplings change with it. The Higgs self-coupling is especially important because it determines whether the potential continues upward or eventually becomes negative. At ordinary scales, the local vacuum behaves normally. At extreme scales, the running coupling may cross zero. That crossing does not trigger decay. It signals that the shape of the potential may contain a lower direction. The vacuum can still remain trapped behind an energy barrier, potentially for periods that make the current age of the universe look negligible. The calculation, therefore, produces a peculiar result. Our vacuum may be unstable in principle, while being effectively safe for any timescale relevant to stars, planets, or civilizations. The difference between those statements is enormous. An unstable chair collapses because ordinary motion carries it toward a lower energy configuration. A metastable vacuum does not need to roll over its barrier. It can tunnel through. Quantum tunneling does not require a particle or field to acquire the energy needed to climb across a forbidden region. It assigns a small probability that the system appears on the other side. For a single particle, the mathematics is already counterintuitive. For a field occupying all of space, the process becomes harder to picture. The transition would involve the formation of a particular configuration, called a bounce. In simplified terms, a region of the field fluctuates into the lower state in Euclidean space-time, creating the seed from which a real bubble can emerge. Most fluctuations would fail. A bubble below a critical size would be crushed by the energy cost of its boundary. Surface tension favors collapse. The lower energy interior favors expansion. Only when the bubble becomes large enough does the balance reverse. Then the wall moves outward. The critical bubble could be microscopic. Its eventual reach would not be. That creates an uncomfortable separation between cause and consequence. The initial event may involve scales smaller than an atomic nucleus, while the result could alter an unlimited volume of space. The bubble does not need fuel. It does not consume matter in order to continue. The difference in vacuum energy provides the driving force. Yet even this description hides a major uncertainty. We do not know what the lower state would contain. In basic versions of the standard model calculation, the Higgs field moves towards values where the effective potential becomes deeply negative. But such extrapolations eventually enter territory where quantum gravity and other unknown physics may matter. The apparent deeper state may be modified, stabilized, or replaced entirely by phenomena absent from the standard model. So when physicists describe the bubble as creating different laws, that phrase requires restraint. Some constants and particle properties could change because they depend on field values. It does not follow that every law would become arbitrary. The lower vacuum would still be governed by whatever deeper theory actually controls nature. The problem is that we do not possess that theory. Supersymmetry, additional scalar fields, heavy particles, or other new interactions could alter the running of the Higgs coupling. They could stabilize the vacuum completely. They could introduce additional minima. They could create new decay channels. Even gravity, usually neglected in the simplest picture, may change the tunneling probability in ways that remain difficult to calculate with confidence. This makes vacuum decay a rare kind of scientific threat. Additional knowledge does not automatically make it larger. New physics may erase the danger, but until that physics is found, the stability of the universe rests partly on extending a known theory into a domain where everyone expects it to be incomplete. There is another reason the apparent metastability attracts attention. The measured parameters do not seem to place us deep inside the stable region, or deep inside an obviously unstable one. They appear near the boundary. That proximity may be meaningless. It may result from measurement uncertainty, unknown corrections, or coincidence. Physics contains many numbers that could have been different and are not. But boundaries invite questions. Perhaps some deeper principle selects parameters near criticality. Perhaps the early universe favored regions capable of long-lived structure. Perhaps anthropic selection matter, because observers can only arise in vacua that survive long enough. Or perhaps the closeness disappears once more precise measurements and better theory are available. None of the possibilities has been established. What can be said is narrower. The same particle physics that successfully predicts collider events also allows, under extrapolation, a universe whose vacuum is not permanent. The calculation does not require an external destroyer. It requires no hostile intelligence, no astronomical collision, and no failure of engineering. It requires only that the field beneath every particle has another state available to it. The next problem is whether the universe itself could have tested this possibility already. For billions of years, cosmic rays have produced collisions more energetic than those created by human machines. Stars have collapsed, black holes have formed. The early universe reached temperatures no laboratory could approach. If high energy could easily trigger vacuum decay, why are we still here? The existence of the universe is already an experiment. Long before the first accelerator was built, nature was producing collisions that exceed anything humans can arrange. Ultra-high-energy cosmic rays strike planetary atmospheres, stellar surfaces, interstellar gas, and compact objects. Some exceed the energies reached by the Large Hadron Collider and have been arriving for billions of years. If an energetic collision could readily push the Higgs field out of its present vacuum, the transition should not have waited for us. This is one reason particle colliders are not regarded as vacuum decay machines. The safety argument is that the universe has repeatedly performed more extreme versions of the same basic experiment. Earth remains here. So do the Sun, white dwarfs, neutron stars, and other systems exposed to cosmic rays. The comparison requires care. A cosmic ray usually strikes matter at rest, while a collider sends two beams toward each other. A collider can place more of the available energy into the center of mass frame, but nature compensates with scale. Cosmic rays have struck dense astronomical bodies in numbers no accelerator could approach. If dangerous products could be created and trapped, stars and planets would have supplied the test repeatedly. Vacuum decay is also not triggered simply by making one point in space hot. A collision can concentrate tremendous energy into an extremely small region. That does not mean it creates the field configuration required for a critical bubble. The Higgs field would need to cross the barrier in a coordinated way across enough volume for the lower energy interior to overcome the tension of the wall. Random sprays of particles are poor at doing that. The distinction is similar to shaking a box of water versus assembling a wave with precisely the right shape. Both involve energy, but only one creates the needed structure. In quantum theory, spontaneous tunneling remains possible, but the probability is controlled by the bounce configuration, not by a simple threshold a collider can accidentally exceed. Within standard calculations, ordinary collisions do not meaningfully raise the risk.
Proposals for forcing decay generally require contrived field arrangements
Or assumptions about new physics
that no existing machine can realize.
So the immediate fear recedes. Then the older universe creates a harder problem. The cosmos was not always cold and dilute. Soon after the Big Bang, matter existed as an extremely hot plasma. Earlier energies were far beyond those in any terrestrial experiment. If the Higgs vacuum is metastable, the early universe should have provided thermal fluctuations capable of exploring dangerous regions of the potential. High temperature changes the shape of that potential. Interactions with the surrounding plasma can add stabilizing effects, making the Higgs field more likely to remain near the electroweak state. Depending on the details, the same thermal history that seems threatening can protect the vacuum. Inflation is less forgiving. During cosmic inflation, space may have an extraordinary rate, while quantum experience fluctuates stretched for crest across macroscopic distances. A sufficiently light Higgs field would not have remained perfectly fixed. Different regions could have received different displacements. If those fluctuations pushed the field beyond the barrier, some patches might have evolved toward the lower state. Inflation would then enlarge those patches. This creates a constraint that does not appear in laboratory discussions. A metastable vacuum can survive comfortably today and still have been vulnerable during the first fractions of cosmic history. The answer depends on the energy scale of inflation, the Higgs potential, and couplings between the Higgs, gravity, and whatever field drove inflation. None of those ingredients is fully known. If inflation occurred at a high scale and the standard model remained isolated, some calculations find that dangerous Higgs fluctuations would have been difficult to avoid. Yet, our observable universe clearly reached a long-lived electroweak state. That survival may mean inflation occurred at a lower scale. It may mean the Higgs had an additional stabilizing coupling. It may mean new particles changed the potential. Or it may mean the approximations used in curved spacetime are incomplete. The important clue is not a detected bubble. It is the absence of one in our past light cone. That absence cannot prove absolute stability. We observe only a finite region, and we exist only in regions compatible with observers. A universe destroyed before galaxies formed would contain no one to report the failure. Survival, therefore, carries a selection effect. Even so, it constrains theories. A model that predicts decay in nearly every region during inflation must explain how a viable region like ours remained. Catastrophe removes observers, but it does not repair a model that makes surviving domains implausibly rare without a mechanism that produces them. The stability problem begins to reverse. At first, the standard model appears to threaten cosmology. Then cosmology begins interrogating the standard model. The existence of an old universe becomes evidence about interactions beyond any collider. A coupling too small to measure on Earth could have held the Higgs field in place during inflation. An undiscovered particle could have altered the running of the Higgs self-coupling. A gravitational correction could have changed the tunneling rate. The universe may have survived because the standard model is incomplete. There are other possible catalysts. Some theoretical studies suggest that small black holes could modify vacuum decay by distorting space-time and lowering the cost of forming a bubble nearby. Other work finds that thermal effects, back reaction, or the scarcity of suitable primordial black holes can suppress the danger. The subject remains model-dependent, and no observation shows that astrophysical black holes are initiating decay. Their continued existence still matters. The universe contains environments with curvature, density, temperature, and particle flux that no laboratory can reproduce. Every ancient neutron star and long-lived black hole narrows the space of mechanisms that would make the vacuum easy to destabilize.
Nature has been trying to break the vacuum for almost 14 billion years, or more precisely, nature has been exposing it to conditions our theories identify as possible stress tests. The fact that our region remains intact
suggests one of two broad conclusions. Either the vacuum is extraordinarily resistant despite being metastable, or additional physics has been protecting it. Both are reassuring at human timescales. Neither answers the deeper question. If a bubble ever did form, it would not be an explosion traveling through an otherwise unchanged universe. It would be a boundary between two definitions of empty space. To understand what that boundary could do, we have to stop thinking about destruction and ask a more basic question. What happens to matter when the vacuum that defines its properties is replaced? Matter is not independent of the vacuum. An electron is a mass how it interacts with the Higgs field. Quarks acquire part of their mass in the same way, although most of the mass of protons and neutrons comes from the energy of the strong force binding their quarks together. The weak nuclear force depends on the Higgs field as well. Its range, its carriers, and the balance between different kinds of radioactive decay all reflect the vacuum state we inhabit. That means a lower energy vacuum would not simply replace the background while leaving matter untouched. The deeper state could assign different values to the same fields. The Higgs field might settle at a value far larger than its present one. Some particles could become much heavier. Others might become unstable. The balance that allows nuclei to form could fail. Even if composite matter remained possible, it might not resemble atoms. The transition would not burn an object or break it apart through impact. Those descriptions assume that the underlying rules remain fixed while energy is added. Vacuum decay would change the rules first. A chemical bond exists because electrons occupy quantized states around atomic nuclei. Those states depend on the electron mass, the electromagnetic force, and the charges of the particles involved. A star shines because nuclear reactions can proceed under a particular relationship between gravity, pressure, particle masses, and force strength. A human body functions because chemistry remains stable across a narrow range of conditions. Change the vacuum, and these systems are not merely endangered. Their definitions may disappear. This is why descriptions of a decay bubble often sound absolute. The bubble wall is not a conventional object moving through space. It is the region where the flow crosses between two vacuum states. Behind it, the vacuum has already changed. Ahead of it, the old state remains. The wall could carry enormous energy, depending on the potential. But the energy release is not the only issue. Even a comparatively gentle transition would be fatal if the lower vacuum did not permit familiar matter. The exact outcome cannot be calculated with confidence because the standard model potential is not trustworthy at arbitrarily high field values. If the apparent lower region lies near scales where quantum gravity matters hot, then the real destination of the field may be controlled by physics. We do not know. The vacuum might settle into another stable state. It might run toward a regime with negative energy density. It might enter a configuration that causes the interior space-time to collapse. Different theoretical models produce different interiors. Some lead to a bubble whose interior expands, while its boundary sweeps outward through the old vacuum. Others produce a region that evolves toward a gravitational singularity. In certain cases, the new vacuum can have a negative cosmological constant, giving the interior the geometry of anti-de Sitter space and causing it to contract on itself. From outside, none of these details offer protection. The wall still expands through the false vacuum if the energy balance favors growth. Local observers do not get to remain in the old state and watch the new one develop at a distance. Once the boundary arrives, they are part of its interior. The geometry of that expansion creates one of the most difficult implications. No warning can outrun the wall. Suppose a bubble forms 1 billion light-years away. If its boundary moves at nearly the speed of light, the first photons carrying evidence of the event would travel only slightly faster. By the time a telescope detected any change, the boundary could already be close behind the signal. Depending on the exact dynamics, there might be no interval long enough for recognition, let alone response. A civilization could monitor every galaxy it can see and still learn nothing useful before the transition reached it. This is not because the event is hidden. It is because information itself is limited by the same speed that constrains the wall. The universe does not provide an early warning channel outside its own causal structure. The scale makes defense meaningless. A bunker would still depend on atomic matter. A spacecraft would still occupy the same vacuum. A black hole offers no obvious refuge because its interior is not disconnected from the underlying fields. And black holes themselves may influence vacuum transitions rather than resist them. Moving away from the origin would fail because the wall expands in every direction. Even if a civilization could travel near light speed, it could not indefinitely outrun a boundary approaching from behind at almost the same limit. No technology can preserve a local set of physical laws against a lower energy state of the fields that define those laws. That conclusion is sometimes exaggerated into the claim that vacuum decay would destroy the entire universe instantly. It would not be instantaneous across all space. Relativity forbids that. The bubble would expand through the false vacuum causally. Regions beyond its future light cone would remain untouched until the boundary arrived. The observable universe is already far larger than any local event can cross in a short time. More importantly, cosmic expansion has carried many regions beyond our causal reach. If a decay bubble formed here, there may be distant domains it could never reach because space between us and them is expanding too rapidly. The reverse is also true. A bubble could already exist beyond our current horizon and never affect us. Or it could exist inside the larger universe but outside the region from which light has had time to arrive. Its relevance would depend not only on distance, but on the expansion history of space-time. This produces a strange fragmentation of fate. Vacuum decay need not be a single ending shared by all existence. Different causally separated regions could remain in different states indefinitely. One domain could disappear behind an expanding wall, while another continues, permanently unaware that the transition occurred. The universe may not possess one future. Inflationary cosmology makes this possibility even more pronounced. Some models describe a background that continues inflating while bubbles of lower energy vacuum nucleate within it. Each bubble can become a distinct region with its own cosmological evolution. If the process never ends everywhere, the larger structure may produce an enormous collection of domains, each associated with different vacuum states. This is one path toward the idea of a multiverse. The concept does not begin with parallel versions of individual lives. It begins with fields, energy landscapes, and regions of space-time that stop sharing the same vacuum. What looks from inside like a universe may be one bubble among many. But that possibility introduces a contradiction. If vacuum transitions are part of cosmology, then a decay bubble is not only an ending. Under different conditions, it can also be beginning. The same mechanism that would erase our physics may have helped create the environment in which our physics became possible. Our vacuum may itself be the interior of an ancient transition? If so, the stability question changes. We are not asking whether an eternal structure could someday fail. We are asking how long one phase in a much larger sequence can persist, and whether the apparent permanence of physical law is only a local memory of the last transition. If our universe began inside a vacuum transition, then the bubble is not merely a hypothetical object moving toward us. It may be the reason there is an us at all. Some models of cosmic inflation describe a high-energy vacuum that caused space to expand at an accelerating rate. That state did not need to end everywhere at once. Different regions could decay at different times, creating bubbles in which inflation stopped and a lower energy phase took over. Inside one of those bubbles, energy stored in the field could be converted into particles and radiation, producing the hot conditions associated with the early universe. From within, the bubble would not look like an object with an edge somewhere in the sky. Its interior could grow into a complete observable cosmos. The boundary would recede beyond anything its inhabitants could reach. What appeared to them as the beginning of the universe might be one local phase change inside a larger inflating structure. This picture is not established fact. Inflation itself is strongly supported by several features of the universe, including its large-scale uniformity and the pattern of primordial fluctuations. But the mechanism that drove inflation remains unknown. Eternal inflation is a consequence of some models, not all of them. No experiment has identified the inflating field, confirmed a landscape of vacua, or detected another bubble universe. The theory remains compelling because it turns several separate problems into one process. A vacuum state drives expansion. Quantum fluctuations cause it to decay unevenly. Bubbles form. Different field configurations may produce different low-energy physics inside them. Some bubbles collapse. Some remain nearly empty. Some expand without forming stable matter. A small fraction may develop conditions in which stars, chemistry, and observers become possible. The universe we see would then be selected twice. First by physics, because only certain vacuum states can persist and produce complex structure. Then by observation, because any beings capable of asking where they are must find themselves in one of the rare regions where asking is possible. That reasoning is known as anthropic selection. It does not explain why the landscape exists or why its rules have a particular form. It only warns that our observations may be biased towards survivable environments. The warning becomes important when physicists notice that several properties of our vacuum appear unusually permissive. The cosmological constant is small enough for galaxies to form. The Higgs field supports particle masses compatible with stable atoms. The vacuum has lasted long enough for heavy elements, planets, and biological evolution to emerge. These facts may reflect a deeper law. They may result from chance within a vast collection of possible vacua, or the apparent coincidences may vanish when a more complete theory replaces the standard model and our current cosmology. Without access to other regions, the alternatives are difficult to separate. Researchers have looked for indirect evidence that our observable universe collided with another bubble in its distant past. A collision before or during the early stages of cosmic evolution might leave broad patterns in the cosmic microwave background, such as unusual circular features or asymmetries. Searches have not produced accepted evidence of such an event. Most observed anomalies can be explained by statistical fluctuations, foreground contamination, or the limits of working with a single sky. That last limitation cannot be engineered away. Cosmology has only one observable universe to measure. There is no second sample for comparison, no controlled experiment in which the vacuum parameters can be changed, and no viewpoint outside space-time from which the larger structure can be inspected. Theories about a vacuum landscape can generate predictions, but those predictions often depend on how probabilities are assigned across an endlessly inflating background. This leads to the measure problem. If eternal inflation creates an unlimited number of bubbles of every permitted type, ordinary counting loses meaning. Every event that can occur may occur infinitely many times. To calculate what a typical observer should expect, one must regulate those infinities. Different methods can produce different answers. A theory that predicts everything somewhere risks predicting nothing, specifically here. The issue is not simply philosophical. It affects whether anthropic reasoning can explain measured quantities. A successful framework must do more than allow our vacuum. It should make our observations reasonably probable without relying on an arbitrary way of counting observers across an infinite structure. No agreed solution exists. Vacuum decay, therefore, sits at the intersection of two uncertainties. Particle physics asks whether the Higgs vacuum is metastable. Cosmology asks whether vacuum transitions create regions like our universe. Each subject borrows assumptions from the other, while the theory needed to join them remains incomplete. Gravity is central to that missing theory. In ordinary quantum field calculations, vacuum tunneling is treated against a prescribed space-time background. But a vacuum carries energy, and energy changes space-time. When gravity is included, the shape and rate of a transition can change. In some cases, gravitational effects suppress decay. In others, they can allow transitions that would not occur in flat space. A lower energy vacuum with negative energy density may not produce an expanding internal cosmos. Its interior may collapse. A transition to a positive energy state could inflate. The geometry of the bubble depends on the difference between the vacua, the tension of the wall, and the gravitational response. At sufficiently high energies, those ingredients cannot be separated. This is where the reassuring lifetime estimates reach their boundary. Within the standard model, and under conventional assumptions, calculation usually places the expected decay time far beyond the present cosmic age. But that estimate extrapolates the Higgs potential into a region where unknown gravitational physics may matter. It is precise inside a theory that is known not to be complete. That does not make the estimate useless. It means the answer is conditional. If no new interaction changes the potential, if the measured parameters retain their current central values, if quantum gravity does not introduce a stronger decay channel, and if cosmological history has been modeled correctly, then the vacuum appears extraordinarily long-lived. Each condition is plausible. Together, they define the edge of what can be claimed. Human activity does not appear capable of moving that edge. Accelerators do not threaten the vacuum. Nuclear weapons do not approach the required field configuration. No foreseeable technology could manipulate the Higgs field across a critical region with the needed precision and energy. The uncertainty is not practical. It is structural. We may live in a universe whose lifetime is effectively unlimited for every civilization that could ever arise. Yet the same equations still refuse to call it permanent. They describe stability as a probability, existence as residence in a local minimum, and physical law as a condition that can depend on where a field has settled. The closer we move toward a final theory, the less obvious it becomes that the universe has one permanent set of rules, and that leaves the last question. If our vacuum is only one state among many, and if transitions between them can create or erase entire cosmic histories, what does it mean to say that the universe will end? The answer may depend on whether we are describing everything that exists or only the temporary region whose laws made us possible. There is a temptation to reduce vacuum decay to a question of survival. Will it happen? When? Could anything stop it? Those are understandable questions, but they are not the questions the physics answers best. The theory does not provide a date, a warning system, or a practical defense. Under current assumptions, it does not describe a threat that should alter any human decision. What it changes is the status of permanence. Most endings in cosmology leave something behind. Stars exhaust their fuel, but their remnants remain. Galaxies fade, But gravity continues to organize matter. Black holes may evaporate, but the fields and particles of the universe persist. Even the heat death of the cosmos assumes that the underlying vacuum remains fixed while usable energy gradually disappears. Vacuum decay is different. It does not wait for the contents of the universe to finish. It changes the condition that makes those contents possible. That distinction matters because nearly every prediction about the distant future begins with an unspoken assumption. The laws measured now will still apply then. We calculate stellar lifetimes using the same particle masses. We estimate proton decay, black hole evaporation, and the expansion of space using constants that are treated as durable. We imagine civilization adapting to a colder, darker universe while remaining made of the same matter. A metastable vacuum weakens that assumption. The equations may remain valid locally for an inconceivably long time. They may outlast every star and every civilization. Yet if the vacuum is not the lowest state, then those equations describe a phase rather than a final foundation. The difference between a phase and a law can be invisible from inside it. Liquid water follows stable rules until temperature and pressure cross a boundary. A magnet appears uniform until its internal order changes. In both cases, the material does not violate physics. It enters another state permitted by the same deeper framework. The vacuum may work in a similar way, although the consequences would be far more fundamental. The constants that seem built into reality could be properties of one phase of reality. Particle masses could be environmental. Force strengths could reflect where fields settled after an earlier transition. What appears universal may be local to our domain. This does not mean the laws are arbitrary. It means the laws we observe may not be the deepest layer. That possibility changes how the universe is pictured. Instead of one permanent arena containing temporary objects, reality may be a collection of temporary arenas generated by fields moving between states. Some vacuum-inflate, some decay, some collapse, some persist long enough for structure. A small subset may permit observers who mistake longevity for necessity. From their point of view, the vacuum would feel absolute. They would measure the same constants in every laboratory. They would see the same particle properties across billions of light years. Their entire observable history would support the conclusion that the rules are fixed. And they could still be living inside a metastable phase. There is no contradiction in that. A state can be uniform without being permanent. It can be ancient without being fundamental. It can survive every test available to its inhabitants while remaining vulnerable to a process. No local experiment can predict in advance. Our universe has already demonstrated extraordinary stability. It produced nuclei, atoms, stars, galaxies, planets, and at least one form of life capable of reconstructing parts of its underlying theory. Whatever the final verdict on the Higgs vacuum, that durability is real. But durability is not the same as certainty. The measured Higgs mass, the inferred top quark properties, and the running of the standard model couplings place us near a region where the answer remains unsettled. Better measurements may move the boundary. New particles may stabilize the potential. Quantum gravity may replace the entire calculation with one in which the dangerous minimum never existed. A future theory may show that the vacuum is absolutely stable. It may also show that metastability is unavoidable. Either result would be revealing. Stability would require an explanation for the mechanism that protects the vacuum across scales we cannot yet probe. Metastability would mean the universe has endured not because decay is forbidden, but because it is improbable. Those are different forms of existence. One is secured by law. The other persists by probability. Physics already accepts this distinction at smaller scales. An unstable particle does not contain a clock counting toward a predetermined moment. Its decay is described statistically. Each surviving instant does not make the next instant guaranteed. It only becomes part of a longer history that was always possible. If the vacuum behaves the same way, then the age of the universe does not testify to permanence. It testifies to survival. That may be all any observer can ever know. No experiment can hold a second universe beside ours and test which vacuum lasts longer. No telescope can see beyond every horizon. No civilization can wait through every possible future. We infer the structure of the energy landscape from particles produced for fractions of a second, then extend those across scales so extreme that gravity, quantum mechanics, and cosmology begin to overlap. The result is not a prophecy. It is a limit on confidence. We know enough to describe how a lower vacuum could nucleate, how a critical bubble could expand, and why its arrival would offer no meaningful warning. We also know enough to recognize where the calculation stops being reliable. Between those two facts lies the actual unease. The scenario is physically motivated, yet its probability depends on physics, still missing from the theory. The universe may be perfectly safe for times longer than language can express. It may be protected by a principle not yet discovered. It may occupy the only vacuum that can exist, or the background beneath every atom may be a state that has simply not changed yet. The opening question was what could happen if a bubble of lower vacuum formed somewhere in space. But space was never the passive setting in that question. It was the thing being rewritten. And if the laws around us are properties of a temporary vacuum, then the deepest uncertainty is not whether the universe has an ending. It is whether the universe we call permanent has ever been anything more than the interior of one long-lived bubble.